Eric Wieser, I can see he's ready, so please go on and present your talk about scalar actions in Lean's Mathlib library.
Okay, can you hear me?
Yeah.
Cool. So I am a PhD student at Cambridge University, and I've been working on various bits of Mathlib, and this is a presentation about the scalar actions in Mathlib. So we've seen Lean 3 already earlier today. It's dependently typed, so similar to Coq. And Mathlib is, at this point, the canonical library for doing any sort of maths in Lean 3. This presentation is specifically looking at the has_scalar type class, which is simple enough to be used quite a lot, but complex enough to demonstrate some of the difficulties that come up with type classes when working in Mathlib. So let's start by looking at what type classes are. We'll use a simple example of multiplication. So Lean has a type class called has_mul that associates a mul operation with a type G and has some notation for it. And then it has a semigroup type class which extends the multiplication and associates some axioms with it. So generally, your type classes will have some data, like operations on your type, and they'll have some proofs, they'll have some axioms about those operations. So this is the first thing you need to do when working with a type class, is declare it. The second thing you need to do is actually use the type class. So now that you've defined what a semigroup is, you can use this type class by putting in square brackets in a lemma name. And that tells Lean that whenever you want to invoke this lemma, it should just search for that type class and find it for you. And as a consequence, you can use lemmas, you can use the axioms of that type class inside the proofs that use it. The final bit of working with type classes is providing instances of them. So for instance, we can say that lists are a semigroup with the multiplication operator being appending, and we already have a proof in Lean that it's associative. Mathlib doesn't have this instance because no one wants to write list concatenation with multiply, but this just demonstrates how you go about constructing instances. So now let's look at has_scalar. It's similar to the has_mul we just saw, but it's parameterized by two types, not one. It provides a heterogeneous operator over these types called smul, which we use this dot notation for, which applies an action defined by the first argument of type m on the second argument of type alpha. We say the type alpha has an action by m. Just as a multiplication that satisfies no properties isn't interesting, so is a scalar action. In practice, we almost always work with the mul action type class, which describes monoid and group actions by adding two proof fields, here one small and mul small. Mathlib provides numerous stronger type classes which in turn extend mul action with additional proof fields, which you can see in this graph here, where each arrow shows a type class on the left being a stronger version of the one it points to on the right. And underneath, I've written down the axioms that they come with. So now let's look at some instances of these type classes provided by Mathlib. We'll start with the elementary actions. So let's look first at left multiplication, where we just define the scalar action of A on B as A times B, where A and B are from the same type. This is fairly straightforward to write down. We just write smul equals mul. And just as we saw, there's that tree of stronger type classes. And so we can promote this to a mul action from a has_scalar if there's a monoid structure. And this kind of thing extends all the way up this tree. So if we go back to this diagram showing all of the scalar action type classes, there's this parallel hierarchy of type classes for multiplication. We saw that if you have a has_mul, you can promote it to a has_scalar. And if you have a monoid, you can promote it to a mul action. But we can do the same thing for semi-ring to semi-module, and there are a few other connections between these hierarchies. Generally speaking, whenever you provide some kind of scalar action in Mathlib, you should try to provide as many of these other classes as possible so that you have as many lemmas at your disposal about this scalar action. Let's look at another scalar action. So this one is the one by the natural numbers, where, for instance, the action by 3 is simply adding the element to itself 3 times. You can define it recursively using Lean's pattern matching. And similarly, if you know more about the structure than alpha just being a commutative monoid, you can put more structure on this action. So if it's additionally a semi-ring, then you haven't just got a NAT module, you have a NAT algebra. Both of these are instances, or in fact, every instance I'm showing here is one that's already present in Mathlib somewhere. We can do something analogous for the integers, where if we also have a negation operator, we can define the action by negative integers as the negation of the action by the positive version. To give us some examples of why this action is useful, it comes up in random theorems and definitions throughout Mathlib. So for instance, if you sum over a set a constant, then Lean can simplify that to just a scalar action times that constant by a natural number. Or when we're defining what it means for a monoid to be Archimedean, we use this scalar action to just denote repeated addition of y. And another example of the integer action, if you have an alternating map and you permute some of its arguments, then the result of that alternating map is scaled by the sign of that permutation. And that sign is an integer, so you can't just directly multiply it by the result of the alternating map. You need to use a scalar action to convert between the types. The final trivial action we'll look at is the one used by 3D vector space, which multiplies each component element-wise. Mathlib encodes R3 as the type of functions from fin3 to R, so this generalizes naturally to an action on all function types. We can provide this instance as follows. If we look at this more closely, though, we've actually chosen a special case. There are many module structures in R3. By using small instead of multiply, we can describe all of them at once. Since our definition of the scalar action is now in terms of another scalar action, I'll start calling this a derived action instead of an elementary action. We use this as an opportunity to switch from looking at elementary actions to looking at derived actions, those which are built out of other simpler actions. So resuming the case we were just looking at, it's just as easy to write down the derived action that does a scalar component, but here we have a small rather than a mul. And as a result, now not only can we multiply our vectors in R3 by elements of R, but we can do so by the positive elements of R or the rationals and many other objects such as subgroups of R, things like that. Sorry, not subgroups, submonoids. And just as we saw before with the multiplication action, there are stronger versions of this when we know more about the action on the elements. So if alpha is an M module, then the functions from iota to alpha are also N modules. That instance was fairly easy to write because functions don't have any proof fields. All we have to do is construct data. If we now look at putting a has-scalar action on linear maps, then things are a little harder. And I'm going to use this as an example to work through how you would go about putting a scalar action on an object of your own and trying to do it in as general a way as possible. So you would start by writing down the fact that you want to produce a scalar that has scalar operator and all the type classes that you need in order for Lean to accept this as a definition. And then you can implement the action just as you did before, but now we have two proof obligations to fill out. And we can work our way through most of the proof obligations, but we get stuck on these points. So we need the action by A to distribute over these terms of type N, and we need it to be two actions to commute. And with our current assumptions, we can't prove that. So the next step we do is we would strengthen one of our assumptions to replace the has scalar with module, and now we have this axiom available that tells us that the scalar action distributes over the addition. But this next one's harder because we don't have any type classes about commutativity of scalar actions yet. We haven't seen those. And in fact, the solution when we get to a situation like this is often just to define a new type class that has exactly the property we need. And that's what Yuri did to solve this problem in the past. So now we've successfully defined scalar actions on linear maps by an arbitrary type, not just the type that is in the linear map. There's one more of these type classes for compatibility between scalar actions, which is this scalar tower. So if you look at these two, the first one is essentially a commutativity axiom, and the second one is an associativity axiom. And this one is useful for things like if you have a vector of complex numbers, it tells you that the action by the complex numbers on that vector the action of the real numbers on that vector factors through the action of the complex numbers on that vector. And this is the type of thing you just need in proofs to factor your actions so that you can then use lemmas about a specific action. And this is scalar tower type class is described in more detail in the formalization of Dedekind domains, where it was useful for working with field extensions. These two compatibility type classes have another surprising application. You can actually use them to axiomatize algebras. So Mathlib provides this definition algebra of module, which takes a module and two extra axioms and promotes it into an algebra. There's another way of building an algebra, but it looks less similar to the things we've looked at so far. What's interesting, though, is if you look at H1 and you remember that we already defined multiplication as an action, we can replace this multiply sign with another bullet. And then this axiom hypothesis is exactly the same as this one. And if we do the same for H2, this hypothesis is the same as that one. So in fact, what we've shown is that if you've got the requirements for an algebra, it's equivalent to replace that algebra with a module, and this is scalar tau and SML class axiom, type class. And why we care about this is it allows us to relax some of these. So before, if we wanted to work with an algebra that didn't have a unit, we were stuck. We would have to write a brand new non-unitable algebra type class. But if we break it apart into these three constituent type classes, we can now just relax the bits we don't care about. So if we want to work in a Lie algebra where there is no unit and the multiplication isn't associative, we can replace our semi-ring with a non-unit or non-associative semi-ring. And similarly, if we want to replace R with something that doesn't have addition, so for instance, we want to scale by the units, we can replace our semi-ring with a monoid and our module with a distributive mole action. And this was useful for actions by units when writing Sylvester's law of inertia. Let's now look at type class diamonds. So consider the following situation. We have an index collection of additive maps from A to B called F, and we want to scale it by the natural 2. What does this SML refer to here? One thing it could mean is the module action inherited element-wise on each additive map, which in turn is inherited from the module structure on B. The module structure on B is the natural number structure we looked at earlier derived from its additive structure. But this natural number structure was available to us on the additive maps too, and even directly on our collection of additive maps. For this example, there are 3 different paths to obtain the instance we need. We call this type of situation a type class diamond in reference to the shapes formed by the arrows. To demonstrate why diamonds matter, consider the similar definition, which scales by the 2 of some arbitrary semi-ring. Are these 2 definitions the same when we set R to n? If we ask Lean, it tells us that it found them by different paths. Of course, just because the path is taken are different doesn't mean that the instances aren't equal. We need to remember that there are 2 types of equality in Lean. Propositional, which is what a mathematician usually means when they say 2 things are equal, and definitional, which is what Lean uses when matching up terms. Until very recently, while double any was propositionally equal to double nat, it was not definitionally equal. As a result, users of definitions like these could end up with an action in their goal state, which was not the one that Mathlib had lemmas about. Sebastian, who we heard from earlier, contributed a fix to this that allowed control of the definitional equality in this situation by adding an extra axiom to additive monoids, in this case, a new NSML field. While it may seem mathematically redundant to add this, it was essential to make the diamond equal definitionally. As in this case, the idea is you populate this NSML field with a definition of the scalar action that you know is consistent with the other ones you're defining. Let's move on to looking at where more work is needed on scalar actions in Mathlib. The has-scalar type class is really intended for left actions, which is apparent in the notation, the constraints about compositions of actions, and some instances of the actions like the multiplication we saw. However, there is a trick to use it to define right actions anyway. There's a type called opposite in Mathlib, which is essentially an alias for just another type, but it has different type class instances on it. So instead of, when you write A times B of the opposite type, that unfolds to B times A. This is exactly what we need, because if we define the right action as taking the opposite before applying the action, then this satisfies all the axioms we need. And this allows us to define the right action of right multiplication, like this, which is now part of Mathlib. And all we're doing is we're taking this opposite argument, we're converting it back to its unopposite version, and we can multiply it on the right. But we're able to satisfy this small condition, because when you multiply the opposites, they swap order. It turns out that if we use opposite for right actions in this way, we have everything we need to start working with bimodules. If we unfold our new syntax, we see that the associativity axiom of bimodules is exactly the SML class we saw earlier. So these were the Lean assumptions you would have to write down to do this. Eventually, Mathlib will likely want sub-bimodules and 2-sided ideals, both of which should now be possible to build using these classes. While we have the tools needed to express action compatibility for bimodules, there are some types of action compatibility that are not expressible with any existing type class, such as this one. Since it's easy to construct multiple cases where it would apply, it is likely deserving of a type plus. So for instance, this is true when A, B, and C are all the same type and both scalar actions are just multiplication, or it's true when B belongs to a submonoid of the type that A and C belong to, or if C is a vector of components and A and B are both scalars. Really, they're just all associativity conditions. There might be a way to avoid this growing mess of compatibility classes. In Lean 4, the multiplication operation is redefined to be heterogeneous, operating over 3 types, not 1. So instead of being a function taking 2 alphas and returning a third, it takes an alpha and a beta and returns a gamma. As a result, it could be used to entirely replace left and right actions, and just use the multiplication symbol for all of them. So for instance, the left action, we just set beta to gamma, and for the right action, we set alpha to gamma. In this approach, the various compatibility classes could become statements about heterogeneous associativity and commutativity, using hypothetical HMOL-SOC and HMOL-LEFT-COM classes to replace its scalar tower and SMOL-COM class. And the condition we saw on the previous slide could be another similar associativity axiom. As we saw yesterday, Mathlib is not ported to Lean 4 yet fully, so while we can definitely experiment with this, we can't fully gauge how this would riffle across all of the Mathlib library. There are also some more diamonds that need to be solved in Mathlib. So while Sebastian was able to solve the module diamonds by natural numbers and integers, there are still diamonds in the algebra instances, because these, as well as having a scalar action, have a canonical map from the naturals to the ring, which, while fully defined by the scalar action, is a separate field to allow definitional control. But exactly that definitional control is causing more problems because now there are diamonds in those definitions. So this could be resolved by adding new axioms to semi-rings, rings, and division rings, just as we added new axioms to adcom monoids and adcom groups. And these would just be defined equal to what the algebra maps already are in a way that doesn't cause diamonds. While I was preparing this presentation, 2 more diamonds were discovered. This is the more interesting of the 2, which is the actions of the units of a monoid on itself, where one path is just via the multiplication action we saw before, but the other path goes through some transitive unit actions. So first we say the action of the units applies to the type itself. Oh, I can't remember how this connects up. Anyway, there are 2 paths to get there, and the path marked X is introducing a definitional incompatibility. And interestingly, the way to resolve that definitional incompatibility would be to have right actions available to us, because that would allow them to be defined equal. So it looks like I've ended a little bit early. Any questions?
All right, thank you. Thank you. If we have more time, that's even better. I can see that there's a question from Kevin on the chat.
So Kevin says, I don't understand why it's better to wait for a quarter Mathlib before experimenting with this stuff in Lean 4. I think that building an experimental algebra hierarchy in Mathlib 4 is accessible and a fun project. I completely agree with Kevin. You should absolutely experiment with this stuff in Lean 4. The only problem is that you have slightly less data available on how effective your experiment will be. Because if you did this experiment in Lean 3, you would have hundreds of existing type classes that would break when you changed it, and you could see how many of them broke and how many of those breakages were broken in a desirable way and how many were undesirable. So while you certainly can experiment in Lean 4, you won't know as much about whether the experiment was the right choice. But I would be very pleased to see someone doing that experiment.
And there's a question from Marcinia.
Yeah, so I guess, yeah, so I've now just learned why NSMOL is there. That's brilliant. I was wondering what that was all about. And I guess one of the issues is that if you're a mathematician and you're looking at the definition of a module, say, and it's got all of these funny fields in them, it seems just a bit bizarre because we don't have diamonds in just ordinary mathematics. Is this an unavoidable problem of computer-based theorem proofs?
So, sorry, specifically, can you, sorry, I lost track of that question.
Yeah, okay. I guess
is it diamonds specifically, or is it the fact that you end up having these extra fields that you don't care about? So you ask.
Yeah, that you have to have extra fields to resolve the diamond issue. Yeah.
Yeah. Okay. So, right. Your question is, is it unavoidable that you end up with these fields that are there only for lean reasons and not for maths reasons, and confuse mathematicians because they think, why on earth is this there? So when this came up, as far as I could tell, there were really two solutions to the problem. One of them is this: put the data in at every level. And the other is force people to take redundant assumptions that they don't want. So either you make all the module structures equal, or you make everyone say, I know that every monoid has a NS module structure, but I'm going to have to write it explicitly anyway. So you never give it to them for free. So lemmas that use, if I go to this slide, the solution here would be to force them to add an extra line here that said module nat beta. And then that way you ensure that you've written your lemma about any nat action, and it doesn't matter anymore that they're not all equal. But that's also unpleasant. You've just moved the unpleasantness from where you define the structures to where you use the structures. And hopefully you have way more people using your structures than you do people defining structures, because otherwise your instructions just used once and it wasn't worth defining much.
All right. Any other questions? So I just wonder how flexible this mechanism is in case there is some kind of structure that you didn't think of when designing the whole hierarchy, and then you come up with something, or someone needs to formalize some merge of different algebraic and, for example, algebraic and topological mixture of something, a theory like this. So how flexible this mechanism would be in such a case?
So this type class hierarchy, oh, I'm echoing. This type class hierarchy isn't set in stone. So for instance, this SML0 thing was added later because someone found they needed it. But you're right that if you have this thing where every time you add a new axiom, you end up with a new type class, then you do get a combinational explosion. And to some extent, you can remedy this by having mixed-in style classes, which is essentially what I was doing for this algebra. Where instead of having new classes for non-neutral algebras or algebras that aren't quite algebras because they don't have a base ring, they just have a base monoid, you split your type class up into smaller pieces which interact with each other, and you only put data in some of them. So here, this one holds all the data, and these only hold proofs. So you've got this trade-off between a combinational explosion of the number of type classes in your hierarchy, or having a large number of arguments to your lemmas, because now you have every condition expressed separately. So I guess at its extreme, it would be like either saying that R forms a ring, or saying that R has a multiplication, an addition, a 0, and a 1, and then having a separate type class for everything that you care about in the lemma, such as associativity or distributivity. And that obviously doesn't scale either. I think it's still an open problem of what will be most convenient, and it's the type of thing that you can experiment more with the lean for.
All right. And another thing that I'm curious, in Mizar library, there was an issue or kind of problem that lattice structures were first defined the algebraic way, and then for some reasons it was more useful to look at lattices as relational structure. So from that time, the library, as if contains two different branches, there are some translations between them, kind of isomorphisms, but they are totally unrelated in a way. So is it any better in lean and in this approach that you could somehow make those two approaches match better, or reuse some more data when you formalize lattices, for example, with two algebraic binary operations as one approach, and as something with a relation on some set?
So as Mario points out in chat, I'm echoing. As Mario points out in chat, in lean, the type classes for lattices have both the relation and the algebraic operators in them, and all the various assumptions proving that they're consistent with each other. So a lot of the time, you could define a type class with very little data and derive all the remaining data from just the data you put in. But almost always it ends up better to put in every piece of data you can think of and then prove that they're all consistent with each other. Because down the line, you might find you needed it to be definitionally equal to something. And the only way to ensure that is to put it in right at the beginning.
I see. Okay, thank you.
And generally, I wouldn't say that Mathlib has any cases where it's gone down two completely different paths and both are iterating in parallel. There are a few things where two paths were taken early on, and one of them has essentially been decided as not the right way to do things and isn't growing anymore and is still there in some sense. But there's no big fork of the community having to do awkward isomorphisms between two different halves of the library, as far as I know, but I can't speak for everyone.
Yeah. Okay, thank you. Any other questions or comments?
You're talking about the deprecated stuff.
I'm talking about the deprecated stuff, exactly.
My PR is about to hit. It builds, but doesn't lint currently.
Yeah.
So that will hopefully become structures soon. But we don't need them. We could just throw them away.
Yeah, that was the thing I was thinking of the only case I can think of where things have gone in two different directions and there's a slight mess left behind as a result. But no one's working with those deprecated things anymore.
Right, that's why the refactor was rather easier than I was
fearing. You can ask Kevin exactly how hard it is to make this kind of refactor when Mathlib is over 500,000 lines of code.
Yeah, I see. And the system is changing, so it also adds some more complications.
Yeah. I've touched 92 files so far, and I've had 2 merge conflicts. I've been working on it about 3 weeks.
So this is the difference between bundled and unbundled structures, right?
Yes, that's exactly it. I'm changing the way that the ones we don't use are implemented.
So what is the advantage? I'm not really clear what the advantage of the new style is. Can someone explain that?
No, I'm not anymore. Now I've done the refactor. I'm rather thinking that we should just delete all the files.
Okay.
I had thought that there was a reason for unbundled morphisms, but I've now realized I can't see one.
Well, there must be. Okay, well, what was the reason for making the change?
The reason we made unbundled morphisms was because we wanted morphisms. that I know. We didn't have any morphisms before then. And this was something that really surprised me about the type theory community. Because I just come along saying, hi, I'm a mathematician, I need group homomorphisms, how do you do it? And the answer is, oh, that's a very interesting question. Well, there's several ways. Just think it's group homomorphisms. How can you not have solved that yet? But somehow it all depends on the system, and it's experiments needed to be done, and it was just an experiment. And then we did another experiment, and one of the experiments won.
All right. Any other comments or questions? So thank you again for the talk.